write the notes. Okay, so that one, please ignore it. And yesterday night, I have uploaded again. Okay.
Okay, sir.
Okay, how many of us are present now? Online, only 12, right? As of now, 12.
11.
11. Okay, 11 is there, including me, 12. Okay, so I will take attendance now. Okay, so Kilit Siring, Gaki, Karmongdi, Kezang, Namit, Punap, Rajesh, and then Roshan. Samjana. Okay, Sonam also present, Tenzin Jamso. Okay, so now let's start our session now. Okay, so since your data may exhaust, right? So waiting for your friends. So if they join, so, okay, meantime it's fine. Okay, so we'll start. We are still at unit 2 only, load frequency control. Okay, so today we'll see on frequency control. So how to control the frequency. So you know why we have to keep frequency constant and then all, right? Okay. Hello. Okay, my request is this no need to mute, but don't speak while I'm teaching. So if you have doubt, you can just ask. Okay, so when you mute, so I feel like as if I am talking to myself. Okay.
Okay, sir.
Okay, so there's but while I'm teaching, so
Okay, sir.
if there
Okay.
is any, so if there is any doubt, you can disturb. But when if you don't have doubt, so please, okay, so just stay silent only. Okay, so now, okay, I will start. We are still at unit 2 only. So load frequency control, and then today's lecture is lecture 5 on unit 2, and then today we will study about frequency control, how to control the frequency. Then before we to control frequency, so you know that why we have to keep constant frequency, right? So everybody knows that how why we have to keep the frequency constant. Okay, so but today we'll see how to control and make frequency control. So this first slide is just like a repetition only. So what we have done in the introduction of unit 2, we know that, okay, so that frequency should be kept nearly constant, or we can say that it has to be kept constant for a good good power, right? Or quality power. So we have to keep frequency constant, and then so particularly this constant frequency is important related to the load like induction motors or synchronous motors. So we have to keep the since we have to keep the speed of the induction motor and then synchronous motor constant. So why we have to keep this speed of induction motor and the synchronous motor constant is because so it is depending on the other parameters or performance of like water, feed water, or fuel. You know that example for hydropower. So now rotation or speed of a synchronous motor will depend upon the discharge. If there is more discharge, speed will increase. If there is less discharge, speed will also decrease. So depending on that, so it depends on. So similarly for steam, thermal power plant, so we have to depend on the fuel. So that's why we have to know that why we have to keep the frequency constant. Okay, so rest all are okay. So just a repetition only. So what we have learned earlier. Okay, so but very important thing is why how we can control the speed is why we have to keep frequency constant. We have already studied, but only thing is now in this lecture we will see why frequency, how to control the frequency. Okay, so now we know that control of generation and frequency, we can call it as a load frequency control, and then LFC we call that. So how to control the speed? So normally, so in hydropower, introduction has been done that we can control the speed of a generating unit by speed governors. Okay, so that speed governor, controlling the speed by using speed governor mechanism, is known as primary speed control. And then there are another speed control called supplementary control, which we have not learned earlier. And I thought you might have learned in machine, but when I talk with your machine module tutor, he says you have not learned this. There is another concept known as AGC, that is automatic generation control, which is known as a secondary speed control. Okay, so which means when we are controlling the speed, it means that we are controlling the frequency also, right? Okay, so there are two ways which we can control the frequency, but primary is speed governor. Okay, so you have learned that PID governor and then all. Then secondary is AGC, so which we learn in detail. Okay, so in later slide, I will explain detail. So first, we'll see how to control the speed by frequency by speed governor. Okay, so let's see one example. So concept or fundamental of speed governing. Okay, so just see this slide. Figure generator supplying a load, isolated load. So you just see that, and then you can see here. So normally here I have written steam or water, but now I will explain in terms of water, because in Bhutan it is famous for hydropower. We don't have a steam power plant. So now I will see that. So input here we have is water, means it will be a discharge, right? Certain discharge will be there. Based on this discharge, this turbine will rotate, right? Or it will rotate, which means speed is there. And then it will develop some torque, which is known as mechanical torque. And then, so based on this, we know that power and torque relation. So we will get a mechanical power, and this mechanical power will drive the generator, and this is how will feed to the load, right? Power will be fed to the load. But here when we employ this, that one first explanation is without the governor. So now when I explain about this speed governing, so we have to control the speed. So if you're not controlling, let's say your discharge is increasing, or you have a very high discharge and then your demand is low, so it's useless to generate this, right? So there is chances that the turbine may get damaged also without. Okay, so now what you can do is, okay, so now employing a governor. Okay, so just employing a governor. So here this, okay, sorry. Okay, so with this governor, so what you can do is, so here, let's see some mechanical power, torque is there, which means there is some revolution is taking place, speed is there. And then here, so generally it will have some reference speed, okay, which we, example, you might have seen that 1500 RPM is rated speed. So let's keep 1500 RPM, and then this one here you will get a measure speed, and then this measure speed you will compare with the reference speed, and then based on this, what it will do is this governor will generate a one signal. Let's keep as a y, that is an actuating signal. So based on this actuating signal, what it will happen is, either this, in hydro turbine, hydro, we call it as a gate. In steam it will be called it as a valve. So based on this actuating signal, this gate will be either open or closed, and this is how we will get the mechanical power. Okay, so then this is a basic fundamental of speed governing. But now let's talk in terms of how to control the speed. So now let's assume that this load means electrical power, right? Power demand has been either increased or decreased. So assume that power has been increased. When power increase, what it will happen is this mechanical, sorry, not mechanical, electrical torque will also change, right? Let's say power demand in this area has been changed, then torque, electrical torque will also change, whereas mechanical torque will remain same because we have considered the discharge same or a stream same. So which means there is mismatch between electrical torque and mechanical torque. So this mismatch will be measured and then compare with this reference, and then this governor will, okay, control the speed. So which means either it will open the gate or close the gate, and then based on this, so again you will get a electrical torque and a mechanical torque same, and then is how power will be generated. Okay, are you getting now? Hello?
Yes,
Yes,
sir.
sir. We're
Yes,
getting
sir.
some.
Okay, sir, you're clear now this
Sir, yes,
concept?
sir. Yes, sir.
Okay. Okay, so this is how, just a principle or fundamental of speed governing. Okay, so once more I will explain here. So now before, okay, so forget about this governing part. Okay, so there will be a discharge. Okay, so from discharge, what it will happen is, so this turbine will rotate here, right? Revolve or rotate at the rated speed or whatever it may be. So when discharge is there, turbine will rotate, and then this will develop some torque, and then when mechanical torque is developed, so it means that power at P equal to omega R, omega T, then it will fed to the generator, and this is how power will be supplied. But this is without any controlling, right? If you have a higher discharge, you can generate more. If you have lower discharge, you can generate low. But we have to see is based on the load. Okay. So if you are not require any power and generating high power or more power is useless. So now what you have to do is, so now let's start from this load. Okay, so load, let's say there is changes in load or demand of power has been changed. When it change, so now similarly this electrical torque will also get changed, means change, and then mechanical torque will remain same because we have kept the discharge same as same. Now there is mismatch between mechanical torque and then electrical torque. So there will be a reference speed we have, that is we normally get 1500 rpm. So, okay, so here torque means in terms of speed. So now this measure speed will be compared with the reference speed, and then what it will happen is, so you will get one signal, means from governor it will control, let's assume that is a Y as a actuating signal. So based on this, so either gate will be closed or open. So in hydro turbine or hydropower we call it as a gate, in stream it will be called it as a valve. Okay, so now based on this valve or gate will open or close, and then this is how we will supply to the load, means we are controlling here, right? This is how it will be controlled by the governing. So this is known as speed, fundamental of speed governing. Okay, so now before we go detail about the speed governing concept, so now what we will do is, so we'll start first without employing the governor. Okay, so this one already I have explained. When there is a load change, it is reflected. Okay, so when there is a load change, it is reflected instantaneously as a change in electric torque output of the generator, which means when there is load change, electrical torque output will also change, which means mechanical torque will remain constant. There is mismatch between mechanical torque and the electrical torque, which in turns result in speed variation as determined the equation of motion. So this equation of motion will be given by this equation. So but for further details, I have written here, refer the book Power System Operation and Control by Kundur. Okay, so page number also I have given, so you can just read how you have got this equation of the motion. So just now you know that equation of motion will be given by J d omega m by dt equal to Ta equal to Tm minus T. Okay, this already I have explained with the diagram. Okay, so then what is meaning of this J and omega mt has been given. Okay, so now when load change, how generator responds. Okay, so we'll see that when load get changes, how generator responds to the load. So we'll see that. Okay, so now already we have said that when load change, okay, when load change means power, load means power, right? Power consumed change. So electrical torque will also get changed, but mechanical torque will remain same, right? Okay, so now there is a mismatch of the electrical torque and the mechanical torque, which means there is a speed variation. So based on this speed variation, we can control the speed. So now already we have learned something about the transfer function in the control system. So now this generator response to the load change can be represented by the transfer function. Okay, so transfer function represent the relationship between rotary speeds. So rotary speed here we have del omega r, which means change in rotary speed, and then function of electrical and mechanical torques. So now, actually this mechanical torque, it is a input to the generator, right? Input, and electrical torque is, actually it is like a output from the generator, right? Because if load changes, what it happen is electrical torque also changes, whereas mechanical torque will remain same. So there is a mismatch between electrical and mechanical torque. When there is mismatch, then there is a speed variation. So this speed variation can be compared here, and then you will get a one actuating, or some call it as an accelerating torque. And then, so this is the turbine or rotor which we can represent here. Okay, so this is a transfer function relation relating the speed and torque. So which means these changes in the speed you will get here based on comparing the electrical torque and mechanical torque. So if there's some error, this error, which we call it as said accelerating torque, so you will get this, and then based on this error, so you will get the electrical, sorry, rotor speed. Okay, okay, are you getting now?
Yes, sir.
Yes, sir.
Okay, okay, so if you are not responding, then I will not proceed further. Okay, so this is generator response to the load, how it generator responds to the load. Okay, so now we'll see. Okay, so this transfer function concept and then all you have learned in the control system. Okay, so I'm very sorry, my laptop is not working much. Okay, faster. So now what we have to do is, just earlier one is a transfer function representation of generated response to the load change. Now for this load frequency studies, what we have to do is, it is always advisable or advised to write the relationship in terms of mechanical and electrical power rather than torque. So we are always talking about the load, so which means power. Actually, it is related, but it is advisable to express in terms of mechanical and electrical power. So now we know that relationship between power and torque is given by P equal to omega T. But here I have written omega R because of the rotary speed. So let it be question number 1. So everybody know that this is a fundamental equation. Okay, equation representing the relationship between power and torque is given by omega rt. Okay, let it be question what, and then so now with changes in load. Okay, so there is changes, considering a small deviation from initial value. When there is changes in load, means there is deviation from initial value. So let's consider that new power P is given by P naught plus del P. So where P naught is a initial power before the load changes, and then del P is a changes in power. Similarly, torque can also be written as T naught plus del T. Okay, so and that is T naught is initial torque, del T is a changes in torque, and similarly omega R. A new rotor speed can be represented by omega naught plus del omega r, where omega naught is the initial rotor speed and del omega r is a new rotor speed. Okay, so now substitute this all in the equation 1. Okay, so equation 1, so P naught is, P is given by P naught plus, okay, so this Okay, just this substitute in the equation 1, equation 2, that power can be substituted there. So then omega is equal to omega naught plus del omega r, and then t naught plus del t. So you substitute this equation 2 to the equation 1. So we will get this one. So now you just expand this. Okay, so just multiply this omega naught into t naught, omega naught into del t. Okay, just multiply this one. And then here, what we are assuming is, so we are neglecting the higher order terms, and then just we'll keep the lower order term for our simplicity. Okay, so then you will get del p is equal to omega naught into del t, because we are neglecting the higher order term omega naught into t naught, so it will become higher order one. So we'll neglecting then t naught into del omega r. Okay, so neglecting higher order term, so we'll get this equation number 3. Okay, equation number 3. And then so this change in power, okay, this change in power can be represented by, okay, so input power we have is mechanical power, right? Here. Minus the output you will get is electrical power, okay, which is equal to, same here, omega naught. So del T means mechanical torque minus electrical torque. Okay, change in torque means mechanical torque minus electrical torque. And then similarly, so initial value, that is TMO, mechanical torque minus electrical torque by del omega r. But what we are doing is, in steady state, okay, so in steady state, okay, so in steady state, this TMO will be equal to TEO, and then we have to know that in steady state omega naught will be equal to 1. Okay, so now just substitute that TMO equal to TEO, so which means here it will become 0. Right, and the omega naught will be 1. That is the condition for steady state. Okay, not in the transient, but we are considering for a steady state, and change in power is given by del Pm minus del Pe, which will be equal to omega naught. So omega naught will be equal to 1 in the steady state, and then this will remain as it is. In steady state also there will be some mechanical torque and the electrical torque. Certain deviation will be there, but in steady state, initial TMO and TE will be equal. So if it is equal, then TMO minus TE will be 0. Okay, so are you getting now? Okay, so if it is 0, then you substitute this, and then you will get the next equation, equation number 5, which will be equal to del PM minus, okay, so del PM minus del PE is equal to del TM minus del TE. Okay, are you getting now? So we are getting this equation number 5. Okay, so 5 after considering the steady state. So in steady state, what you are getting is initial value will be equal to 0, and then initial frequency omega naught will be considered 1. So now I said, so it is advisable to represent in terms of power instead of torque. So now using this equation, so now we can get a figure 2. So that figure 2 can be expressed in terms of power and electrical power and mechanical power. So this is how we will get the block diagram of representing the changes in power, okay, electrical and mechanical power, and then you will get in terms of speed. So where m, it is known as a inertia constants, and but this m will be equal to double of the twice the h. Okay, so this is a transfer function relating speed and power. Earlier one is transfer function only, but it is relating the speed and then torque, but it is advisable, okay, for your easy understanding. So always it is advised that you have to express in terms of power, not in terms of torque. Okay, so now from here what we have to understand is, within the range of speed variation, which means till now earlier one, okay, so first fundamental of speed governing, we have considered about the governor. But here, what you have to know is, here we are studying without considering any governing system. So just we have seen that if load changes, if there's no governor, what it will happen, just we have seen that. Okay, so now without governors, see here, within the range of speed variation with which we are concerned, the turbine mechanical power is essentially a function of valve or gate position independent of frequency. It means that, so without governing system, okay, so what we have to do is, okay, we will get is this mechanical power is essentially a function of valve or gate position. Okay, so what which it means is, so if there is no governing system, which means it will not detect the deviation of the speed, so it depends on only the mechanical power. So now to develop higher mechanical power, so it depends upon either gate or valve opening. Okay, so if you want to develop more mechanical power, so you have to open more gate or valve, which means there will be more discharge. If you want less mechanical power, so this is how we can control the load in earlier days one only. Okay, so without employing the governor. Okay, so are you getting now?
Yes,
Okay,
sir.
any doubt? Okay, so if you are clear, still we are considering without the governor, but we have studied the concept of governor, so later on we'll apply, but this is how without employing the governor, so we can control the speed also. Speed, it means that, which means just by opening the gate, valve or gate. Okay, so this is how we can control the speed. So if you control the speed means we are controlling it to the controlling the frequency. Now we'll see today again. Now we'll see the load response to frequency deviation. If there is changes in frequency, how load will respond. Okay, so in general, everybody will know that load. When we talk about the electrical load, you will see varieties of electrical device. So normally you might be famous of resistive load. Most of time you might have seen the resistive loads such as lighting and heating loads. So this load are, we call it as a resistive load. So always we use this, right? Day to day life, we use lighting and heating loads, and electrical power is independent of frequency. In such case, it's fine. It's independent of frequency, we can say that. But in case of motor loads, mostly this motor load is a factory load, right? And then in household also, you might have seen a little bit of the fans. So in terms of motor load, electrical power changes with frequency due to change in motor speed. So what it will happen is this electrical power will also get changes due to change in motor speed. So if there is higher speed, so you know that power generation will be more. Less speed means less. So now it depends on this motor speed. So now let's assume that overall frequency dependent characteristic of this electrical composite load here means load which has a resistive as well as inductive load, which means motor load and all. So can be expressed by this equation. Del PE will be equal to del PL plus D del omega R, where del PL means non-frequency sensitive load change, like resistive load like lighting and heating load. Okay, and then d omega del omega r is a frequency sensitive load change like motor, fans, and then all. And then d, what is this? D is a damping constant. Okay, so just now you know that, okay, electrical load, okay, which depend on frequency characteristic of, can be represented by this equation, that is del PE is equal to del PL plus D del omega R. So what is del PE? Say, you know that composite load, electrical load, and then del PL is a non-frequency sensitive load change, and then this part is a actually frequency sensitive load changes, and then D is a damping constant. So this non-frequency resistive load, sensitive load are example lighting load, heating load, and then these frequency sensitive load changes are like fan and then pumps, so on. Okay, so this It's a general equation representing the electrical power. Okay. Okay, so then, so with this one, so now we'll see how it, if there is changes in frequency, how this load will respond. Okay, so this is a general equation which we can represent. Okay. Okay, next. So now we are talking something about, okay, before we see that how it responds, so now we are talking something about the damping constraints. So what is mean by damping constraint? Okay, so you know that what is mean by damping. We have learned in the automatic control system what is mean by damping. So now damping is a damping constant. It is expressed, okay, so expressed as a percentage change in load for 1% change in frequency. It means for every 1% change in frequency, what is a percentage change in load? Okay, damping constant. So normally this damping constant will be in between 1 to 2%. So I have given one example also, 1 to 2%. If D, if somebody says D equal to 2, it means that 1% frequency change in frequency would cause a 2% change in load. What it means is 1% change in frequency would cause a 2% change in load. If damping D is equal to 2, it means that 1% change in frequency would cause a 2% change in load. Or if damping equal to 1% change in frequency would cause a 1% change in load. Okay, depend on this. So now based on this damping, using damping constant, so we can represent a system block diagram of a control system by giving this one. Okay, so already we know that this is a mechanical power, this is a non-sensitive electrical load frequency power, and then you just see that this is a damping constant employing, and then this is a our rotor transfer function, rotor, which can be represented by 1 by ms. M is a 2h. Okay, so then you will get the same. Just we have copied this, and then here now extra thing is what we are doing is we are employing the damping constant since there in the load. Okay, so there is a damping, right? Okay, so what is damping and all we have learned in earlier. Okay, so now with this one, this block diagram can be by using the control system concept. So you can reduce this block diagram. Okay, so you can reduce this block diagram. So everybody knows how to do a reduction in block diagram. So now this can be reduced and then make in this form. So this, you can reduce this and then you can make that 1 by ms plus d equal to this. This concept we have learned in the control system. So now using the block diagram reduction technique, so we have reduced and then make in this form. So now from here you can see that without employing any governor, okay, so in the absence of speed governor, here also we are saying without employing speed governor, how load responds to frequency deviation. So see here, in the absence of speed governor, the system response to load change is determined by the here inertia constant D, inertia constant sorry M, and then damping constant D. So it depends fully on inertia constant of the rotor and then damping constant of the your rotor. Okay, so then what it means is this steady state speed deviation is such that the change in load is exactly compensated by variation in load due to frequency sensitivity, which means so these all are the manual control of frequency. Okay, so now without employing any. So now this is okay. So now everybody is going for faster control, right? Manual control to automatic control. So now what we have to do is, so now we have to see by employing the governor. So that is known as isochronous governor. Okay, so general name it has been given is isochronous governor. So governor, you have different types of governor, PID when you open. Okay, but here just we'll see the isochronous governor. What is meant by ISO here? They have given actually governor is to control the speed, but isochronous means constant speed. To maintain the constant speed, we are employing the governor. So which means earlier it is done manually. Now we will see by using a machine, right? Governor, that is isochronous governor. And then isochronous means constant speed. So now see here in figure 6. Okay, so in this figure 6, you can see here clearly that, okay, so let's say, so we can represent in terms of power, right, instead of torque. So we can see here mechanical torque. From where it has been generated? So this, from turbine, you will get the mechanical torque, and then this mechanical torque is used to drive the electrical generator, and then this is how we produce the electricity or power. Okay, but here employing a governor means actually this is a basic concept of the governor. So what you will do is, this is a governor. Okay, so in this one, so you will measure this governor will measure the speed, okay, WR, okay, speed, and then it will compare with this reference speed omega naught, and then you will get some difference, that is del omega R. Okay, and then this governor will, what it will do is, this governor will amplify, okay, so amplify this del omega R, and then you will get one signal which is known as del Y, and it is called it as actuating signal. And then this actuating signal will be used to either open the valve or gate, valve in steam turbine, whereas for hydro turbine it is called gate. So it will either open or close the gate, okay, so depending upon this actuating signal, and this is how it will control the mechanical power. So now if it require more mechanical power, so gate opening will be more based on this reference, okay, this error. And then what you will get is, so mechanical power will also be more, then with this, then electrical power generated will also be more, okay, right? And if you require a less mechanical power, so this actuating signal, okay, based on this difference in the speed, so it will close the gate or valve, and then similarly your mechanical power will be less, and then so electrical power generated, it is dependent on the load. Okay, so now if you explain from here, from load side also it will remain same. So now if your demand is less, okay, very low, we require low mechanical power, right? So which means, so speed will get changed here, and then it will compare with reference speed, and then this will amplify this error, this difference, and then you will get one signal, actuating signal. Based on this, so your gate will be either closed or open, and then this is how mechanical power you will get. So this call, okay, so here I have explained here in figure 6 shows the speed governing system. Okay, earlier one we have only done for this portion. Now we are employing additional one, that is governance. Okay, so it's measure rotary speed. Okay, W omega R is compared with the reference speed omega naught, and then this error signal, or we call it as a speed deviation, is amplified and integrated to produce, okay, it will be amplified by using again K, and then integrated to produce a signal, or we call it as a control signal, del Y, which actuates the main steam supply valves in case of steam turbine, okay, whereas for gauge in hydraulic turbine, it will open the gauge or gauge in the hydraulic turbine. Okay, so are you getting now? So now what it has is, very interesting thing of the governor is, it has a reset action of this integral. So once you have done this, so it will not remain fixed, it will keep on resetting. Okay, so then again you will get another signal, so it will be integrated and produce one control signal, again it will reset, and then keep on doing this. Okay, so because of the reset action of this integral controller, del Y will reach to a new steady state when the speed error omega R is 0. So now when you will get this, when this measure rotary speed and the reference speed is 0, then only we can get the, okay, so it means it will reach to the steady state. Okay, are you getting now? Hello?
Yes, sir.
Yes,
Getting, sir.
Are you getting now?
Getting, sir.
Yes,
Yes,
sir.
sir.
As far
Getting.
as far as possible, so just in the meantime I have to interrupt you. Earlier one I have uploaded different lecture note on the lecture 5. So please ignore that one and then use this one, earlier one. So it is similar, but what you can see is you might find very difficult. So it seems most of you are struggling in power system operation and control. So now, as far as possible, I try to simplify this. Okay, so this much I can do. Okay, further simplification may not be possible. If possible, I will try to simplify, but this much I can simplify and then make you understand more. Okay, so now this isosynchronous, when we talk about the isosynchronous, so you said that there is advantages of isosynchronous and then all, but there is one. Okay, so before we start, so now this isosynchronous, what it will work is, so for a generating unit, it says that with isosynchronous, if you have employ a isosynchronous governor in one generating unit, so what it will say is when subject to a load increase, so you will get this type of response of a generating unit with isosynchronous. So what it means is the increase in P means PE, which means electrical power, causes the frequency to decay at a rate determining the inertia of the rotor, which means when power increase, electrical power means load increase. So see here, when power increase, so now it will decrease the or decay the frequency. This frequency means speed, right? So it will decay this, and then what it says is as the speed drops further, when it it drops, the turbine mechanical power will try to increase or begin to increase. This is because we have to compensate that, because load required is more, right? Which means power, mechanical power required is also more, right? But why speed is decreasing? Because more load. So then to compensate that, mechanical power will be increasing. Okay, so it will begin to increase as soon as frequency decays. Okay, so what it's done is in this in turn causes the reduction of rate of degrees of speeds. Rate of rate of degrees of speed will decrease, whereas increase the speed when the turbine power is axis of power, means when there is a more power, then turbine, we know that the speed of turbine is more. Okay, so now the speed will ultimate this. Okay, so first it has been in degrees, and the mechanical will try to compensate this, and then so this speed will again rise to the, okay, or return to the reference speed omega naught. Okay, so at the steady state is, so now load and then power, mechanical power will be equal now in this case when it return to steady state, means there's no changes in load. Okay, so which means here the speed will ultimately return to its reference value, and then steady state turbine power increases by an amount equal to the additional load. So here what it says is when your load increase, okay, first your frequency will decay, which means your speed will decrease, and then to compensate that decrease, what it will happen is it will try to increase the mechanical power, and then it will bring back to the your original speed, or we call it as normal speed at the steady state. Okay, so this it will depend on or amount, it will increase. Okay, the speed will ultimately return to its reference value, and then steady state turbine power increases by an amount equal to the additional load. Similarly, if you decrease the load, so it will be function same. Okay, so similar to this. Okay, so now we have talked about the isochronous governor. Okay, so these are the advantages. It can control automatically, but one disadvantages of this isosynchronous governor is it works satisfactory when a generator is supplying an isolated load or only one generator in a multi-generator system is required to respond to the changes in load. In this case, what is saying is this isosynchronous governor will work only for a isolated load, or generator is supplying isolated load, or if there is a parallel connection of generator, then it will not work. Okay, so this is only for a single unit. So example, Chuka has a 4 unit. So if you employ for only one unit, then you can use this type of governor. But if you all want to synchronize this 4 unit, then this type of thing will not work. So now what we have to do is, so for this, so power load sharing between the generator connected to the system means there are 4 unit, let's say Chuka 4 unit. So now all 4 unit has to share the load equally. So in such case, this type of governor will not work. So now what you have to do is you have to add the governor which called with the speed droop characteristics. There will be speed droop characteristic must be provided. Okay, so which means power load sharing between generators connected to the system. So speed droop characteristic must be provided. Since isochronous governor will work only for a single generator. Okay, are you getting now? This is the disadvantages. Now we'll see the speed governor with speed droop characteristics, which means this type of governor is applicable for a grid connected one, right? Other one is only isolated one, that isochronous governor. So now governor with speed droop characteristics, which can be employed for a grid connected or multiple generator connected in the grid. Okay, so now this isosynchronous governor cannot be used when there are 2 or more units connected to this system. Okay, since each generator would have to have preset same speed setting, so that's why it will not be applicable for a multiple generator. Okay, so but it can be used only for an isolated system. So what it says is if we employ this isochronous governor to a multiple generator in a grid, so what it will have is, there's no technical word as such, but it says they would fight each other. It says they would fight each other. What it means is each generator will trying to control system frequency to its own setting. Okay, which means if one generator has been given to load, let's say 20%, so he will try to bring back to that 20% only. Rest he will give to other generator. So again, other generator has been also set their limits, so which will not be able to do this. So in such case, what we are doing is we are employing the governor with the speed droop characteristic, which means actually working principle will remain same. Only thing is governor with speed droop characteristic means there is a improvement in the governing system. Okay, so which we can control all the generator connected to the grid system. So it has been said here, multiple load division between 2 or more unit operating in parallel, governors are provided with a characteristics so that the speed droops as load is increased. Okay, so see here, now we'll see with this basic block diagram of a speed governor with droop characteristics. So now others, everything remains same, but here first diagram you see figure 8, governor with steady state feedback system. So what you will have is same. So earlier one we have learned only about this one, right? So we have learned this much only, but this one is applicable only for a single generator. But now what you have to do is, so there in a system, let's assume that there are numbers of generator connected or multiple generator connected in parallel. Oh, we know that condition for parallel. So now in such case, what you have to do is, see this governor will get modified. Okay, this governor will be get modified, and then we will connect with one additional device, that is R in a block diagram, and that is known as a droop. Okay, here it is represented by R, droop. Okay, so this governor in a steady state, other function will remain same. Okay, so like earlier one explanation, working will remain same. Only thing is, for multiple connection of the generator, so this isochronous governor is not functioning. So then we are provided this with the droop characteristic R. So now just bring this governor only, first block diagram with steady state feedback. So just bring the governor. So integrator means in a control system you have learned 1 by S, right? In terms of Laplace, we can represent like this. Then K is a gain, and then you see that speed omega R and the droop characteristic R. So this is the governor, okay, not a whole system. Okay, upper one is a whole system, but this one is a governor with a droop characteristic. that blue one I brought down here. Okay, so this is a governor, and then you see that using a block diagram reduction techniques, everybody knows, right? Or you have forgotten or not, I'm not sure, but we know that by using a block diagram reduction technique, so we can write this omega del r is equal to minus 1 by r 1 by 1 plus stg del r. Okay, so this tg is 1 by kr. Okay, so if you are not able to understand this, so you just open the control system notebook, reduction of the block diagram, and then you see that how you have got this one from figure number A, 9A, and then how you have got the 9B reduced block diagram. So you have to employ. So now see here, speed loop characteristic, or we call it as a regulation characteristic also. Some call it as a regulation characteristic, some call it as a speed loop. That's why it has been represented by R, maybe obtained by adding a steady state loop around the integrator as shown in figure. Okay, so around this figure integrator, so we'll employ the steady state feedback loop R, so to get the speed loop or regulation characteristic. So now this transfer function of the governor, this governor only, I'm talking about the governor of figure 8 reduced to the form shown in figure 9. Okay, so means first you will get in this form. Okay, so it's very easy. This summation we have brought here, so input to this summation is del omega r, then what is there after that k, then after that is integrator, and then from there it has been connected r, and the output you are getting is one actuating signal del y, right, which will be amplified by this integrating amplifier, and then okay, amplified. Okay, so this, okay, so then this type of, so now you see that B, this type of governor is characterized by proportional controller with a gain. So gain here you are getting is 1 by R. So this type of governor is characterized as a proportional controller with a gain of 1 by R. So this is known as proportional controller, and then you are getting gain 1 by R. Okay, are you getting now?
Yes,
Okay. Okay, so then what you have to do is, okay, so now we have to find the percentage speed regulation or droop. Okay, it is called as a percentage speed regulation or a droop. So now for this one, you see the figure. Okay, so now just see the figure 10. Okay, so in figure 10, you can say that. Okay, so actually we are trying to find how to find R here. So the value of R determines the steady state speed versus steady state speed, which means in terms of frequency in y-axis, versus the power, or we call it as output power, or output power is also depending on the valve or gate position of a generating unit is shown in figure this one. So now what is mean by speed droop? It means a ratio of speed deviation or frequency deviation del f, okay, ratio of frequency deviation or speed deviation to change in bulb or gate position del y or power output del p. Okay, so what is this R mean? Speed deviation R is equal to change in frequency by change in power, or we can also call it as a change in valve or gate position. Okay, so whereas this del f can be written as frequency f minus f naught. Okay, so this R is referred to as a speed regulation or droop. Okay, so some call it as a speed regulation, some call it as a droop, and then it can be expressed in terms of percentage. How you will express in terms of percentages? Percentage speed or frequency change divided by percentage power output change. Okay, so which means, see here power means here we don't have load, 0, so no load, steady speed. Okay, so in no load, and then as a load increase, what it will happen is speed will keep on decreasing. Everybody knows that when load increase, speed will decrease. And then we can consider that in no load, so we have a speed somewhere here. Okay, so we have kept just not an exact one, but this is a speed at no load. And then when load keep on increasing, which means here it will be speed at full load. Here we have loaded to 100%, 1 per unit. So what it will have is, okay, so this is a speed at full load, omega fl. Okay, so then if you minus this no load speed minus full load speed divided by nominal speed or rated speed, then we will also get a percentage regulation, or we call it as a droop. Okay, are you getting now? Okay, so now if you are required to find some changes in power in this one, so del P we can get from here. So how much it has been changed, the frequency. If this much power, let's say del P has been changed, then let's assume here it is a P1 and then here as a P2. So a power changes is P2 minus P1, which is equal to del P. So see here, in P1 you have certain frequency here, and then P2 you have another frequency. This is how frequency has been changed, right? So based on these changes, we have to find the percentage change, and then we have to control the change in the speed, which means indirectly we are controlling the frequency. Okay, are you getting now? So we'll give one related one example which you have learned in the machine. So load sharing by parallel units. So you have learned this in the electrical machine. DC, I'm not remembering DC or AC, but you might have learned this load sharing by parallel units. Okay, so I have seen even you have solved numerical example also. Okay, so now if there are two units, so let's say in machine you might have learned as a two synchronous generator, or you might have learned as a, okay, but here we'll talk in terms of unit 1 and unit 2. If this unit 1 and 2 are operating in parallel, okay, if unit 1 and unit 2 is operating in parallel, so this unit 1 and unit 2 has to share the load equally, right? So in machine you have learned that two identical generators has to share a this much load, and the rating of generator 1 and then generator 2 is this much. It has been written at what frequency it will share, and then some, but like this you have learned this. But here what you have to do is unit 1 and unit 2. Okay, so if two or more generator with droop governors characteristics are connected to a power system, there will be a unique frequency at which they will share a load. So we know that, right? At what frequency this load will be sharing. Okay. Then consider two units with droop characteristic as shown in figure. So now we'll consider the two unit 1 and unit 2. Okay, unit 1 and unit 2 as shown in this figure 11. And then, so let's say initially unit 1 is supplying power P1 and unit 2 is supplying power unit P2. Okay, they are initially at nominal frequency. So when power P1 and P2, so you see here their frequency is omega naught when they are supplying it. Now, when a load increases, okay, del PL causes the unit to slow down, which means when load increase, both the unit will try to decrease or slow down. The governor increase output until they reach a. So what it will do is when speed increases decreases, there is a speed deviation, right? So when there is a speed deviation, this governor will function now. When governor function means governor will try to increase the output and then find out at which frequency these two unit will share the load. So now just now let's assume that, so when it changes to P1 dash and P2 dash, so now frequency org is operating at the F1 dash, which means both the unit are operating at the same frequency. Initially at F0, when load increase, this governor will try to function it and then try to operate at F dash. Okay, are getting now?
Sir.
Okay, then what it will say is amount of load picked up by each unit will depend upon the individual droop characteristics. So now we can say that the frequency it has to operate is here, F1 dash new frequency, but how much load this unit 1 will pick up and unit 2 will pick up will depend upon their droop characteristic. Okay, so which means at least they will share at a certain common frequency. Okay, then with this, so we'll see some derivation on small derivation. Actually, you have done in the machine, but let's revise back. Okay, so now let's see that from the above figure, you see that del P1 will be equal to P1 dash minus P1, which will be equal to change in frequency del F, which will be equal to change in this frequency divided by R1. So what is R1? Actually, this R1 is a rating of a unit 1. So unit 1, it might be rated at 100 MVA or it may be 50 MVA and then all, right? Then similarly, del 2 will be equal to P2 dash minus P2, and similarly it will remain same because changes in frequency is remain same because F naught minus F dash. So this is changes when load increase, and then it will depend upon the 2. So now if it take a ratio del P1 by del P2, so you will find R2 by R1. Okay, so if you take a ratio, then what it means is, okay, so if the percentage of regulation of unit are nearly equal, okay, so that if droop characteristics are nearly equal, the changes in the output of each unit will be nearly in proportion to its rating. Okay, so its rating, okay, so its output of each unit will be nearly equal to nearly in proportion to its rating. So that's why you might not have noticed that in machine, so when you get one generator sharing example 1.33 MVA a megawatt, then another generator it will be somehow near to this 1.66 like this. Okay, so it will not vary. Example, if you have one generator sharing 1.3, another cannot share the load by 5 or 10 megawatt like this. So which means percentage of regulation of unit are nearly equal. If it is equal, then changes in output of each unit will be nearly in proportion to its rating. Means so see here del P1 is indirectly proportional to its rating, and then del P2 is indirectly proportional to its rating. So which means, so in machine what you have learned is most of time this rating is same. Two generator of capacity 50 megawatt or MVA, you might have seen that same rating, and then how it will share the load by load of 3 megawatt. So in question you might have solved like this. So in that case you might have get around 1.33 1.6 like this. This is because of this concept in machine you might not have learned. So okay, so if there's rating is same or rating same is there is speed regulation or droop percentage of regulation or droop of the unit are nearly equal, then the change in output of each unit will be nearly proportional to its rating. Okay, so are you getting now?
Yes, sir.
Okay, so what I have planned is, so today I will keep this much with this. Okay, so this time response and then all, you can try to see that it is just showing that how it will go back to the steady state only. So with this, today I have planned to stop here, and then if you have doubt, so I will give some few minutes. If anyone has a doubt, then I will explain once more. Any doubt?
No, sir.
No doubt. Okay, then, so now,
So
okay,
it's
so
like
now I,
upload video, sir.
this one is uploaded. Earlier one I have uploaded. Okay, so, but that one you can ignore that. Okay, so this one I feel compared to earlier one, this one is much simpler. I try to make simple as far as possible. And then earlier one compared to earlier one, this one is simple. Okay, so earlier one I have deleted and this one already uploaded in VLE. So you can just go through that, and then I will also create the VLE forum, so you can ask doubt whatever you want, okay, there, okay, related to academic. And then moreover, what I feel is this is just like an engagement only. So when you come back, I think we may have to again do face to face this all thing. Okay, I may have to teach again. Okay, so but when we teach here, so I think it will be much faster. Okay. Okay, so with
Okay,
this,
sir.
Okay, sir.
with,
Thank you,
with
sir.
this,
Thank you,
we will.
sir.
Okay, so with this, we will stop our lesson for today, and then hope. Okay, so you are getting enough network connectivity. Okay,
Yes,
and then
sir.
my only worry is, so some of your friend Kilowangchu has never signed into BLE, so please inform to him if there is any problem. It is not compulsory that you have to come online always here. If there is no network, no need to come. But what I feel is, okay, so if you have some problem, please at least inform to us, or I will try to solve your problem, whatever problem you have. I will try to solve this. Okay, so but problem is you some of your friend has never logged into BLE, so that's the concern. I'm okay. So even when you are here, also you have not signed in. So please inform your friend. Okay, so like Kilewang Chu on it, Kilewang Chu. Okay, so that's all from my side. Okay, so you stay safe. Okay, so thank you very much.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.